Hello students, this is your professor Dr. Mink. And guess what? Welcome to another lecture, another exciting lecture for CSC223, Comp Sci 2. And this is our last video lecture of the class. And the last topic we're going to be covering is graphs. Let's get started. Three main topics we'll be covering, none of which I expect you to understand at this point or yet. We'll cover directed and undirected graphs first, weighted graphs second, and then we will finish with common graph algorithms. Like with trees, graphs consist of nodes and the connections between those nodes. The structure is a little different, but we're still going to use nodes. And in graph terminology, the nodes are referred to as vertices, and they refer to the connections among the vertices as edges. Vertices are typically referenced by a name or a label, and edges are referenced by a pairing of the vertices. So for example, if we have vertices A and B, the edge that connects A and B would be AB. An undirected graph is a graph where the pairings representing the edges are unordered. Here's a graphic depiction of an undirected graph with vertices A, B, C, D, and the edges that connect those vertices. And I mean, if you want it, well, we could. We'll list them out. You've got edges AB, AC, BD, BC, BD. Some more terminology. An edge in an undirected graph can be traversed in either direction. And two vertices are said to be adjacent if they have an edge connecting them. So adjacent vertices, those that have an edge connecting them, are referred to as neighbors. And an edge of a graph that connects a vertex to itself is called a self-loop or a sling. We haven't seen that yet graphically depicted, but we will. An undirected graph is considered complete if it has the maximum number of edges connecting vertices. A path consists of all of the edges, or the sequence, sequence is important, of the edges that can connect two vertices in a graph. The length of a path is the number of edges in the path, or the number of vertices minus 1. So take the path from A to B to C, okay? Number of vertices is 3, and there's two edges, one between A and B and one between B and C. So number of vertices minus 1, 3 minus 1 is 2, or the number of edges. An undirected graph is considered connected if for any two vertices in the graph, there is a path between them. Now, if you recall the undirected graph that we saw a few slides back, we had A and B, B and C, C and D all connected. We had A to C connected and C to D, B to D connected. But we did not have a connection between D and A. And therefore, that undirected graph was not considered connected. Here is another example of an undirected graph that is not connected. We have a path between A and B, B and C, C and A, and A, B, and C, but we do not have a path between A and D, B and D, or C and D. A cycle is a path in which the first and last vertices are the same and none of the edges are repeated. A graph that has no cycles is called acyclic. Now let's talk about directed graphs. A directed graph, also sometimes referred to as a digraph, is a graph where the edges are ordered pairs of vertices. This means that the edges AB and BA are separate. In other words, they're directional edges in a directed path. Obviously, we're going to look at this in much more detail. Now remember, one of the differences between a directed graph and an indirected graph is that the edges in an undirected graph can be traversed in either way. They're unidirectional. That's not the case with a directed graph. So here we have a graphic depiction, our first graphic depiction of a directed graph that has vertices A, B, C, and D. It also has edges AB, AD, BC, BD, and DC, all of which are directional. They can only be traversed from the first vertex to the last. So the edge AB can only be traversed from A to B. That's not to say that we couldn't also have an edge that was BA, but it would not be the same edge. It would be a separate directional edge. So some of the definitions we used for terms associated with undirected graphs change slightly for directed graphs. So for example, a path in a directed graph is a sequence of directed, one-directional edges that connects two vertices in a graph. A directed graph is connected if for any two vertices in the graph there is a path between them. If a directed graph has no cycles, it's possible to arrange the vertices such as vertex A precedes vertex B if an edge exists from A to B. So remember, in directed graphs, each edge is one directional. And so here we have two directed graphs. One is connected, the one on the left, and the other is an unconnected graph. The left is connected because each vertex is connected and continuous all the way back to 1. In the case of the second, there is no continual path or cycle from 1 to 2 to 3 to 4 to 5 to 6. When you get to 6, you cannot get to 1 from 6. So it is an unconnected path. And when you traverse, let's say counterclockwise, you can get from 1 to 6, but you can't get to 5. Next, we take a look at a weighted graph, sometimes called a network. It's called a weighted graph because it has weights or costs or magnitude associated with each edge. The weight of a path in a weighted graph is the sum of the weights of the edges in the path. And weighted graphs come in either undirected or directed versions. So for a weighted graph, we represent the edges with a triple, including the starting vertex, the ending vertex, and the weight. In the example we're about to see, we're going to have, I can't remember if the 120 is distance or I believe it's cost. So we have a vertex Boston, a vertex New York, kind of starting, location, and destination, and then the magnitude or the weight between the two. You'll see in just a second. Just hang on. So here you go. Hopefully just seconds ago you heard me talk about weighted graphs and the triple, and if not, whatever time it took to eat the Twinkies or whatever you ate, you're back. So the example I was alluding to is this one, in which we use an undirected network weighted graph to represent flights between cities. And the weights are the cost. So Philadelphia to Boston, 219, Boston to New York, 120. In order to get to Roanoke from Philadelphia, you have to fly to New York and then Roanoke, or to Boston, then New York and Roanoke. Now, obviously, the previous example was an undirected graph in which the paths were multi-directional, but here's a directed version of the same graph that could potentially show different costs depending on the direction. So I guess from Philadelphia, Boston, it's more desirable to go from Philadelphia to Boston so they could charge more. That's 219. And from Boston to Philadelphia, it's 199. Or maybe it's a supply and demand thing. From New York to Boston is 140. Boston and New York, 120. Philadelphia to New York, 205, 225, the inverse. So you get the idea of how this network could be implemented with a weighted graph, either directed or undirected. Now that we've explored the structure of directed, undirected graphs and the terminology associated with those, let's take a look at or begin discussing common graph algorithms. There are several algorithms that apply to undirected, directed, and or weighted graphs. And these are used for, there's various traversal algorithms, algorithms for finding the shortest path between two vertices, algorithms for finding the least costly path in a network, and algorithms for answering simple questions such as connectivity. There are two main categories or types of graph traversal algorithms. Breadth first, which behaves much like a level order traversal of a tree. We'll go over each of these. And depth first, which behaves much like the pre-order traversal of a tree. However, there is one difference between a tree and a graph. There is no root node present in a graph. So graph traversals don't have to start at the root. They can start at any vertex in the graph. A breadth first traversal for a graph can be constructed using a queue and an iterator. And we're going to look at an implementation of a breadth first traversal in a minute or two. We'll use the queue to manage the traversal and the iterator to build the result. So an overview of the breadth first traversal algorithm goes like this. In queue the starting vertex and mark it visited. And loop until the queue is empty. Dequeue the first vertex and add it to the iterator. Enqueue each unmarked vertex adjacent to the dequeued vertex and mark each vertex enqueued as visited, and continue to loop until the queue is empty. Before we look at any code, let's walk through a breadth first traversal of this directed graph. And let's start at 2. A breadth first traversal or search for a graph is very similar to the breadth first traversal of a tree. The only catch here is, unlike trees, graphs may contain cycles. Those are the circular motions. So we may come to the same node again. To avoid processing a node more than once, we will use a Boolean visited array. So for simplicity, it's assumed that all vertices are reached from the starting vertex. So let's look at an example using the graph on this slide. In this graph, we start traversal from vertex 2. When we come to vertex 0, we look for all adjacent vertices of it. 2 is also an adjacent vertex of 0. See the cycle? If we don't mark visited vertices, then 2 would be processed again, and it will become a non-terminating process. So a breadth first traversal of the following graph is 2, 0, 3, 1. Okay, students, I'm going to walk you through an implementation of a graph class and a breadth first traversal of that graph. So we're going to start off with creating a new graph named G, and it's going to have 4 vertices, and then we're going to call the add edge method 1, 2, 3, 4, 5, 6, and 6 times 0 to 1, 0 to 2, 1 to 2, 2 to 0, 2 to 3, and that will get us here. 0 to 1, 0 to 2, 1 to 2, 2 to 0, 2 to 3. Okay, see it? And then 3 to 3, the cycle. So, and then we're going to call the breadth first traversal method, and we'll pass to the starting vertice. So I'm going to give you this code. So I'll just walk you through what it does. Here's the constructor. These are all integers. We're going to use a linked list as part of this. Here's our add edge function, breadth first traversal. It's pretty straightforward. The files you're going to get from the textbook are, in my opinion, way too complex for this point in the conversation. So I sourced this from, well, never mind where I got it, but anyway, this is a really good beginner level graph traversal demo. So I'm going to run this. I have some breakpoints that will allow us to walk through this. So here we are at adding an edge. If I look at my variables, you're going to see there's our G, and it's a linked list, and it's got 4 elements in the list, and right now they're all empty. Those lists are all empty. So after we add, let's add 2 edges, 0, 1, 0, 2. Back and look at our variables. Okay, 0 has an edge 0, 1 and 0, 2. So let me see if I could do this without screwing this up. Okay, 0, 1, 0, 2. These are still empty. Okay. Now we're going to add an edge from 1 to 2. That's this edge here, 1 to 2. Go back to my variables. One now has an edge to 2. 2 to 0. Go back in my variables. 2 to 0. My phone's ringing in the back, and we're just going to have to ignore that because I have got too much time set up in this demo, and I'm not going to go answer because I don't even know where it is. My wife's out, so we'll just deal with it, right? It's a pandemic when I'm doing this video. So let's add, whoops, an edge 2 to 3, and then 3 to 3. And if we go back and look at our graph now, 0 to 1 edge, 0 to 2 edge, 1 to 2, 1 only connects to 2, 2 to 0, 2 to 3, 2 to 0, 2 to 3, and last but not least, 3 to 3. Okay, so we're going to just print the header that we're anticipating, and then we're going to call the branch first traversal method, BFS. And we pass to the starting vertex. So we create, here's where we use our Boolean, and it's called visited. It's an array of Booleans, and you'll see how that works in a second. We're going to create a queue for the traversal using the linked list class. So if you come back up here, here's our visited array of Booleans. Here's our queue, which is empty, and let's go back. So S is currently 2. That's where we're starting, right? So we're going to mark that true, and we're going to add 2 to the queue. So if we look at 2 in the visited array of bools, it's now true, and we've added 2 to the queue. And once we do that, we're going to basically print this out, and we're going to then use an iterator to continue to follow through this. So if I look at my output, there's our 2 because we visited that, and then we're going to create an integer iterator I from that value, and while I has next, which we know it does, int n equals I dot next. So now n 0, and here we go. So we'll continue to walk through this. S is now we visited 0. Okay, and we're going to walk through. This is kind of hard to do this graphically because it is
kind of. So after we're step down through a couple more, in our queue is 0 and 3. 0, 3 have been visited. We'll continue to walk through these. And if you look at your output, there's our 0, second that we visited. Okay, and now, oops, not there yet, sorry. We'll get there right now. So now we visited 2, 0, and 3. You can imagine what's next. While I dot has next, yes it does. So and we're going to get to the point where everything is visited, and we're going to print out the last item. And now our queue size should be 0. It is. Size is now 0. So we're done. And our output is 2031. I know that's a lot, but I'm going to give you this file. What I did was I just put it all, I put the driver program all in one Java class file. So this is easy for you to look at.
Now let's take a look at a depth first traversal of the same graph. And a depth first traversal for a graph is, as you might have guessed, similar to a depth first traversal of a tree. The only catch here is, unlike trees, graphs may contain cycles, so we may come to the same node again. And in order to avoid processing a node more than once, we're going to use a Boolean visited array. So for example, in the graph depicted on this slide, let's start the traversal from vertex 2. When we come to 0, come to vertex 0, we look at all adjacent vertices of it. 2 is also an adjacent vertex of 0. If we didn't mark visited vertices, then 2 would be processed again, and it become a non-terminating process. So a depth first traversal of this graph is 2, 0, 1, 3. The depth first search is an algorithm used for traversing or searching tree or graph data structures. The algorithm, in the case of a tree, starts at the root node, or in the case of a graph, we pick an arbitrary node, and then we explore as far possible along each branch before backtracking. So the basic idea is to start from the root, or in the case of a graph, an arbitrary node, and mark the node and move to the adjacent unmarked node, and continue this loop until there is no unmarked adjacent node. Then backtrack and check for all unmarked nodes and traverse them. Finally, print the nodes in the path. The depth first traversal algorithm is rather straightforward, and it starts with a recursive function that takes the index of a node and a visited array. The index of the node is going to be the arbitrary vertex that we choose to start with. If you stay with the example we've been using, we started at 2, and the visited array obviously is empty. You mark the current node as visited, and you print the node. Then you traverse all the adjacent and unmarked nodes and call the recursive function with the index of each adjacent node. And eventually, the visited array will have all the nodes in it, and we can stop. I'm going to show you a coded implementation next.
Now we're going to take a look at a depth first graph traversal. I have a driver program. It's a little more sophisticated than the one I used on the last one. This is going to allow us to do multiple depth first traversals on that same graph that we're familiar with already, but this is going to allow us to start at a new vertex each time. So if we go back to that graph, if you recall, when we started at 2, we can get to 0, we can get to 1, we can get back to, and we can get to 3. And so from 1 we can get to 2, which gets us to 0, which just gets us back to 2 to 3, right? If we start at 0, we could get to 1 to 2 to 3. So, but what happens if we start at 3? There is no path to any of the other vertices. So let's take a look at this. So this, most of the work is done here by this recursive function DSF util, and it takes a node, marks it visited, prints it, and then using an iterator it checks all the adjacent nodes or vertices. So I've got a breakpoint at a convenient point in this program, so let's take a look at what we have. So if I go to 2, right, which was what we did before, we're going to start at vertex 2. Let's look at our memory real quick. Okay, there's our array of booleans: false, 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 false. Vertex 0, vertex 1, vertex 2 has not been visited, and we have our linked list already set up by all the edges. So vertex 0, you can get to 1. There's a path from 0 to 1 and 0 to 2. Let's go back. 0 to 1, 0 to 2. There is a path from 1 to 0. There it is, 1 to 0. From 2, I could get to 0 or 1. From 2, I could get to 0. I get to 1. Okay? I'm sorry. Wrong. From 2, I could get to 0 or 3. I'm looking at the index numbers, not the actual values. From 2, I could get to 0. I can get to 3. But from 3, I could get to 3. There's only a path from 3 to 3. So let's take a look. Okay, so we're going to mark visited v equals true, and we're starting at vertex 2. So if I come back to visited, 2 is now true. Okay, we create our iterator, and while I.hasNext okay, here we go. Whoops. And n equals I.next. It's now 0. That's the first adjacent vertex. And we're going to recursively call that. Okay. Visited v equals true. I forgot to show you, we already printed out to the first vertex. And now 0 is printed out. We're going to go recurse again. Call all of its adjacent vertices. Now we're on 1. Checking them all to see if they've been visited. And here we are at v is 3. It's now true. So we visited them all. But they've all been visited. Now it's going to ask us to run. So starting at 2 is 0, 1, 3. Let's try a different one. We'll say, let's try vertex 3. And create a new graph. We're going to add all our edges, and then we're going to go call DFS start integer 3, and immediately calls the recursive function. So we're going to mark visited 3 as true and print that. And now, while i.hasNext, so what does it have? N is 3. If not visited, recursively call. Well, 3 has already been visited, so we're going to skip that, right? There is no hasNext. We're done. The depth first traversal starting at vertex 3 is just 3 because it can't get anywhere else. We're going to try another one. We'll start at 1. Now let's talk about 1. Okay, 1 can get to 2, 2 get us to 0, and 2 can get us back to 3. So this should not be a problem. I'm just walking through this all. From 1 we can get to 2, we get to 0. To 3. I'm not going to run all the possible scenarios, but you can, because I'm going to give you these files. It's going to contain both traversals in the same package.
Next, we'll talk about the concept of connectivity. A graph is connected, key term, if and only if for each vertex v in a graph containing n vertices, the size of the result of a breadth first traversal at V is n. So for example, starting vertex A with 4 vertices. The breadth first traversal at V, or A, is 4, B is 4, C is 4, D is 4. So obviously the second graph on the right hand side of this slide is not connected. Look at D. Look at A, B, and C. They should all be the size of the result of each of those traversals. Breadth first traversal should be 4 if it were a connected graph.
A spanning tree includes all the vertices of a graph and possibly all of the edges, but not absolutely. In other words, it may contain all the edges, but it doesn't have to. By definition of a spanning tree must include all the vertices. And since trees are also graphs, for some graphs, the graph itself will be a spanning tree, and thus the only spanning tree. Let's take a closer look at this. Now, let's discuss a minimum spanning tree. A minimum spanning tree is a subset of edges in a graph such that every vertex is connected and the sum of the edges is minimized. Let me state that again. The minimum spanning tree is a subset of edges in a graph such that every vertex is connected and the sum of the edges is at its minimal value. So in this case, we have a graph represented on the left as a network and a minimum spanning tree on the right. You'll see on the right, the sum of the weights of the edges is less than or equal to the sum of the weights for any other spanning tree for the graph. In other words, the sum of the weights of the edges is at its absolute minimum value. Here we have an overview of the algorithm for a minimal spanning tree. We start by picking a vertex, an arbitrary vertex at which we will start and add it to our MST, minimum spanning tree. Then we add all of the edges that include our starting vertex to a min heap ordered by weight. Remove the minimum edge from the min heap, the edge that has the lowest weight, and add the edge to the new vertex, add the edge and the new vertex to our minimum spanning tree. Add to the min heap all of the edges that include this new vertex and whose other vertex is not already in the MST. And we will continue until the min heap is empty or all vertices are in the minimum spanning tree. There are two different approaches to determining the shortest path in a graph. The first approach is to determine the literal shortest path between a starting vertex and another vertex, in this case called the target vertex. And that is the least number of edges between the two vertices. And the simplest approach to do this is a variation of the breadth first traversal algorithm. Or secondly, we could look for the cheapest path in a weighted graph. And in this approach, we're going to use a min heap or a priority queue, storing vertex and weights pairs. Here we have two strategies for implementing graphs. First is adjacency lists, and the second is adjacency matrices. So with an adjacency list, we use a set of graph nodes, and each graph node contains a linked list storing the edges within the node. And then for weighted graphs, each edge would be stored as a triple, including the weight. For adjacency matrices, and we're going to go over these, obviously, we use a two-dimensional array. Each position of the array represents an intersection between two vertices in the graph. And each intersection is represented by a Boolean value indicating whether or not the two vertices are connected. Let's take a closer look. Depicted here is an adjacency matrix for an undirected graph. And the undirected graph is depicted on the left, and you can see it has vertices A, B, C, and D, and paths between those, or edges. So remember, an adjacency matrix uses a two-dimensional array, and each position of that array represents an intersection between two vertices in the graph. And each intersection is represented by a Boolean, true or false, indicating whether or not the two vertices are connected. So if we look at this adjacency matrix, you've got A sub A is false, because obviously A sub A is not connected to A. It doesn't have a loop. So A sub B is true. A sub C, true. A is not connected to D. It does not have an edge between A and D, so that is false. B sub A, true. B sub B, false. B sub C, true. B sub D, true. I'm not going to walk through the remaining half of this matrix, because you can walk through that yourself, but hopefully you can see the pattern here. Next, we have an adjacency matrix for a directed graph. And you can see A sub A false, A sub B true, A sub C true, A sub D false, and so on and so on. So notice D in this directed graph is false for every edge connection. So I have a graph program with adjacency matrix class built in, and I've tried to draw the graph and the edges that correspond with my driver program. And here's the main right here. So what we have is and I apologize, I'm not the most artistic person. I know that they're okay, but those edges are a little bit non-horizontal and non-vertical, but anyway. So we're adding edges 0, 1, 0, 2, 1, 2, 2, 0, 2, 3. And then I print the adjacency matrix, and you could see. So the way this works is you have to assume the column headings are 0, 1, 2, and 3. You see the row headings are 0, 1, 2, 3. So 0 to 0 is false, 0 to 1 is true, 0 to 2 is true, and 0 to 3 is false. 1 to 0, true. 1 to 1, false. 1 to 2, true. And 1 to 3, false. And then 2 to 0, true. 2 to 1, true. 2 to 2, false. And 2 to 3, true. And then 3 to 0, false. 3 to 1, false. 3 to 2 is the only edge involving that vertex. That's true. And then 3 to 3 is false. Okay, students, now let's take a look at a program run. So I've put a breakpoint here after we add our first edge so we could take a look at the memory. So I'm going to run this in debug mode. And let's take a look at our variables. Okay, here's our adjacency matrix. Number of vertices is 4. And if you recall, we added edge 0 to 1. So zero to 1 is true. And everything else so far is false. So yep. So now let's step over, sorry. Add a new edge. I added 0 to 2. Okay. 0 sub 1 is true. 0 sub 2 is true. So you can see the adjacency matrix being built. I'll run 0, 3, 1, 2, 2, 0, 2, 3. Whoops. Let's take a look at our memory. False, true, true, true. From 1 to 0 is true. 1 to 1 is false. 1 to 2 is true. And 1 to 3 is false. 2 is true, true, false, true. So we should be able to draw this, right? So let's do this. Let's see if I can get them both in order here. Yes. So we should be able to draw this. 0 to 0 is false. 0 to 1, true. 0 to 2, true. 0 to 3, true. 1 to 0, true. 1 to 1, false. 1 to 2, true. 1 to 3, false. 2 to 0, true. It's already there. 2 to 1, true. 2 to 2, false. 2 to 3, true. 3 to 0, true. 3 to 1 is false. 3 to 2 is true. It's already there. There you go. There's our adjacency matrix, and there's a graphic depiction of that. So let's just say we want it 3 to 1. Right? We didn't add that edge. Let's go back and let's there's our run. So let's go back. We wanted to add 3 to 1. Three to 1. Is it 3 to 1? Yeah, 3 to 1. I will save this. And I'm just going to run it now. Okay. Now it's 3 to 1 is true. There you go. So let's begin to summarize our lesson on graphs and adjacency matrix. A graph is a data structure that consists of two components. One is a finite set of vertices that are also called nodes. Second, a fixed set of ordered pairs, in this example xy, that define edges. So the connection between x and y, the vertices x and the vertex y, vertex x and vertex y, if there is a connection between those two, that defines an edge. And in the case of a directed graph, the pair is sequenced such that xy is not the same as yx. Remember, a directed graph has directional edges. A directed graph is also called a digraph. When a graph is directed, an edge has a magnitude, can be considered a weight, a value, a cost to get from one vertex to the next. If you recall, when we were talking about a graph that had destinations for flights, plane flights, airline flights, and in that particular instance, I believe the weight of the directional graph was the cost of a flight from one vertex to the next, or for one destination, Philadelphia to Boston, Boston to Rhode Island, etc. Graphs have many applications, but primarily they're used to represent networks. And those networks may include paths in a city. If you think about the Google Maps algorithm, it is a massive network, and the path chosen from one destination to the next with many parameters, including traffic updates, toll avoidance, etc., are all used, are processed using graphs. Graphs are also used in social networks, such as LinkedIn and Facebook. So for example, in Facebook, each person is represented with a vertex or a node. And each node is a structure and contains information like person, personal ID, the name, gender, and locale. And then as you connect with other users, right, you build a path. You build an edge between you and another
vertex or node. There are two common representations of a graph. The first we've just finished exploring, which is the adjacency matrix. And the second is an adjacency list, which I'll go over in a second. There are other representations. One is an incidence matrix and an incidence list. The choice of a graph representation is situational, and it totally depends on the type of operation that needs to be performed and the ease of use. But these two, the adjacency matrix and the adjacency list, are the two most common representations of graphs. There are pros and cons to using an adjacency matrix versus an adjacency list. Let's go over the pros and cons. They are easier to implement, and the representation is easier to follow. Removing an edge takes O of 1 time. And queries to determine if there's an edge from vertex A to vertex B are very efficient. O of 1. Cons, they consume more memory space, O of B squared, even if the graph is thin or sparse. In other words, it has a low number of edges. It consumes the same space. And adding a vertex is O of B squared time. So those are considerations when choosing an adjacency matrix versus an adjacency list. So for an adjacency list, we implement it with an array of lists. And the size of the array is equal to the number of vertices. So let the array be called array. And an entry, array sub I, represents the list of vertices adjacent to the vertex I. So for example, if it is array sub 1, all of the vertices adjacent to 1 would be included in the list in index 1. We can also use this representation for a weighted graph. The weights of the edges can be represented as lists of pairs. Obviously, we're going to take a look. I just found one. So I was going to draw one. I actually started to draw one, but I found one on the internet that we can use because my artistic skills are not great. Here we have a graph at the top of this slide and the adjacency list for that graph. And I'm going to show you the same graph with the adjacency matrix next so you can compare the two. So in this case, we have an array size is 5. And that is the same, that matches the number of vertexes we have, vertices. So we'll just trace a couple. 0, index sub 0 holds 1 and 4. 0 has an edge 0, 1, and 0 is contained in an edge 0, 4. Index 1, 1, 0, 1, 4, 1, 2, 1, 3. Index 2, 2, 1, 2, 3. Index 3, 3, 1, 3, 4. Sorry, I almost lost track. 3, 2. My eyes are not young eyes. I've been doing this for a long time. Got my first job as a programmer in 1985. Yes, I'm that old. So um, my eyes have taken the toll. Index 4 holds a list of 3, 0, and 1. Now we're going to take a look, to wrap this up, we're going to take a look at the same graph in the adjacency matrix. Although adjacency lists are not as easy to read, the representation is a little bit more cryptic. Adjacency lists are efficient in their use of storage because we only need to store the values for the edges. So for a sparse graph that has millions of vertices and edges, this can mean a lot of saved space. On this slide, we have the same graph with the same edges and the adjacency matrix for that particular graph. You can take a close look. If you want to take the program that I'm going to give you, you can do that. You could code those edges in the driver and then run the adjacency matrix and see that, that output. My friends, that brings us to programming project 24.3. From your textbook, it asks you to complete the implementation of a graph using an adjacency matrix that was presented in this chapter. And here is, instead of showing you the program, here is the driver I used to build each edge. And there is the adjacency matrix that graph generated from that graph. Now, I'm sitting here thinking this is most likely our last assignment, so I'll give you some extra credit. It just popped into my head, and let's just call me spontaneous. So, Professor Spontaneous, build an interface for this that prompts you for the vertices. Obviously, you're going to have at least 2 vertices, or you don't have a graph. And then we'll continue to prompt you. Make it an ask before iterating loop. And let me see. How about I will test it with at least 10 vertices when I run your program, and we'll make that an extra 20% extra credit opportunity. Okay? And of course, don't hesitate to ask me questions. Thanks.